All right, welcome back. We're going to look some more at statistics here. And what we're going to work on right now is standard deviation. So we're going to actually run through, and we're going to have a very small data set here just because this works the same for big data sets as it does small data sets. And we need a few numbers in order to do this properly. But we're just doing this as an example. If I had a big data set, I would never do what I'm about to do by hand. With that said, there are going to be a couple places where I'm going to ask you to kind of do this by hand, or you're going to have to do this by hand. But generally speaking, we go to computer systems of some sort to do that for us. TA84 will do that. Most graphing calculators will do that for you these days. Excel and Google Sheets and Numbers will do these calculations for you. And then we have a whole slew of statistical softwares that will run these analyses for us. And that's actually when I have a lot of heavy duty analysis to do, that's where I go, is one of those other platforms instead of trying to do this by hand. Because doing this by hand, it's an enormous amount of work and there's a lot of calculations and it's easy to make mistakes. So even with that said, I'm going to have the calculator do a lot of the heavy lifting for me. So I have 5 pieces of data here, which means that n equals 5. Now the first thing we need to talk about is, or the first thing I'm going to talk about is the degrees of freedom. Degrees of freedom is always n minus 1. So in this particular instance, it's going to be 4. Now, if you're wondering, what does degrees of freedom mean? Degrees of freedom means how much data are we actually dealing with in this set. And I can give you a big, long description, but really what we're dealing with here is that we have 5 pieces of data, which means our degrees of freedom is 4. It's going to be 1 less than the actual amount of data we have in this set. And the larger the data set, the less, it's always, this number is always going to be 1 less than that, but we're not really finding the average. We're going to do some derivatives here, or not derivatives, we're going to do some dividing here with this n minus 1. And the larger the data set, of course, the less that has an effect. So with really large data sets, minus 1 doesn't have much of an effect at all. So we can kind of play around that once we get to a large data set, and it helps us out a little bit. But for smaller data sets, it does make a big impact, whether we're going to do n minus 1 or just n. Here we're saying the degrees of freedom means how many values do we have, because when we do this process, we're going to find the average. And so some of what I'm talking about here is just kind of a pseudo process. I just want to make sure that you kind of get an inkling or understanding of what we're dealing with. When we do the average here, one of these values is going to be decently close to the average. And that's going to be kind of the basis, or the mean rather, that's going to be kind of the basis for how we do the rest of our calculations. So that one value that's kind of right there in the middle is kind of standardized, or if it was a perfect data set, one of these numbers here would be equal to the average. And that reduces the number of pieces that are non-zero when we start to do other calculations, which means we have one piece that is relatively close to 0, which reduces our degrees of freedom by 1, because we have that one piece that is decently close to being 0. Now what I mean by that is I'll show you here in a second. First thing we want to do is find x bar, which means we want to find the average of all these pieces. So I'm just going to grab my calculator and I'm going to open my parentheses, 490 plus 550 plus 480 on down the line. Okay, and yeah, this is a boring data set. It's not necessarily created or tied to anything in particular. I just have a few numbers I need to deal with here. And I'm finding the mean, so I'm going to divide by 5, which is how many pieces of data I have, which tells us that 512 is my mean. Now, in order to find standard deviation, now keep in mind that when we talk about all these different values, you may see mu talking about the mean. The mu is the ideal average, or the ideal mean, okay? This is the mean for the entire population for what our data set is talking about, but we don't have the entire population represented. We have a subset, which means that we can't get the ideal mean. We have to use an adjusted mean, or a partial mean here, which is why we're not using mu, we're using x bar. So we're going to use x bar in place of mu because we don't have the ideal, we only have an approximate. So this is approximately what the ideal mean would be. How much is it off? Don't really know. That's not important to the discussion, okay? And some of you think, oh, well, it seems like it would be important to the discussion. Statistically, we work with what we can. We can't find the ideal mean. It's impossible with a large data set for us to be able to do that. If you're talking about thousands, hundreds of thousands of data points, it is impossible for us to find all those data points and use every last one of them. It's not mathematically feasible to do that. The calculations are so tough when you're doing that much computing. So because of some of the other stuff we're going to do here. So that's why we go with a subset and why we use x bar, which is hopefully a good representation of the ideal. Okay, so we'll go with it from there. And if you have additional questions, please reach out and I can try to explain that in a little bit more detail. Now, then along with that is this symbol right here, right? Which is what we use. It's a Greek symbol for a lowercase sigma here, and we use this for the ideal standard deviation, okay? But the thing is, we don't normally know, we can't find the ideal standard deviation because standard deviation is based upon the mean, and we don't know the ideal mean, so we can't find the ideal standard deviation. So what we're going to use is lowercase s. Lowercase s is equal to s squared, or the square root of s squared, right? And s squared is variance. Okay, it is the variance. Now, why would we need to know about variance? Well, variance is where we're all going to, I'm missing a letter there. There we go. Variance is kind of telling us about the span. That's really what S is telling us. Is the span of our values. They go from where to where. How much encompassing is that value for us? So S is equal to S squared, which makes, the square root of S squared rather, which makes sense. But I'm doing that because S squared is the variance, and that's the actual calculation that we're going to do here to find S. And the way we do that is by taking 1 over n minus 1, which is, n minus 1 is our degrees of freedom like I was talking about earlier, and times the sum of all of the subtractions between our actual values and our approximate average. Okay, so this is where k is going from 1 to n. Okay, this symbol right here just simply means the sum. So we're just going to sum all these pieces up. So this is a uppercase sigma, and it's representing add up all these pieces starting with k equal 1 and going up to k equal to n. In this case, n is going to be 5. And we're just going to do all those other subtractions. So I'll write this out in longhand here. So this is going to be 1 over 4 times the summation of each of these pieces. So k equal 1. Now, theoretically, we would do this in order, but it doesn't really matter. So I'm just going to start at the right. And you say, it doesn't matter? No, it doesn't matter really at all because we're just doing these calculations and we just need to do all of them. So this would be k equal to 1, k equal to 2, k equal to 3, k equal to 4, k equal to 5. Those are all my data points. So here I'm going to do 490, I forgot my 9 there, 490 minus 512, okay, oh I forgot something here, I forgot my square, oopsie. And I'm going to square that, and then we're going to do plus 550 minus 512 plus 480 minus 512 plus 520 minus 512 squared plus 520 minus 512 again. All right, and that's this piece right here is this piece. Those are the same thing. We're just adding those things up. Now the question then becomes, well, how do I find that value? You do it like this, all right? We're just going to go through. Now notice that all these individual values are going to be positive. Every last one of them is going to be positive because we're squaring all of them. So I'm going to do 0.25 times 490 minus 512 squared plus 550 minus 512 squared plus 480, need to put my parentheses in there, minus 512 squared plus 520 minus 512 squared plus 520 minus 512 squared. Okay, now if you've been following along to this point and you're just fine, I would actually encourage you to pause the video at this point and just to kind of make sure you can get this typed in properly on your calculator and that you end up with the same value that I end up with. So I end up with 770 there. So I find that s squared is equal to 770. Exactly. Okay? Now, what does that mean? Well, this means this is your variance, which is an indicator of how close your data set is to each other. You know, how much variance do you have in the entire data set? Now, you can't necessarily correspond that with, well, that means that there's 770 units between the highest and the largest. No, you can look at this very easily and say our largest value is 550 and our smallest is 480. That's not a difference of 770. That's not what this means. This is really just a number that kind of gives you an inkling of how closely set together is this data set. We can use the median or the mean to describe this data set. And once we've chosen the mean, then we can start talking about using variance and standard deviation to talk about describing this as well. And one of the things we need to do is to decide whether median or mean is a better descriptor. In this instance, we're not necessarily talking about having that discussion. We're just picking one and working with it here. So s squared equals 770. Now, if I want s, I just need to do the square root of that. So I'm going to do second square there, and then I'm going to do 770. And that tells me I have 27.748 is my standard deviation. Again, this is my ideal standard deviation. This is my found or my calculated standard deviation. Now, what does that mean? Well, look at my data set. I'm telling, we found that the mean was 512. So if we do plus 20, let's go ahead and say 28, just because we're dealing with whole values here. Plus 28, that would mean that we're dealing with that'd be 540, wouldn't it? And then if we do minus 28, one standard, so this is one standard deviation above and one standard deviation below. And if we do that, we end up with 512 minus 28, which is 484. Now, if you look at our values, that is almost our entire data set. If we were to put these in order, the only things it wouldn't include would be those two values right there. The rest of our data set is included in one standard deviation above and below, which is kind of what we're normally looking for. We understand we really want most of our data to be contained within one standard deviation of the mean, which normally happens when we do this calculation. And we normally find that from there, you'd be talking about two standard deviations. So two standard deviations above would be plus 28 a second time, which takes us up to 568. And another standard deviation, two standard deviations below would take us down to 484 minus 28 would be 456, at which point all of our data is contained within two standard deviations of the mean, which means that our data set is fairly close to itself. Now let's just say for a second we change one value. Let's just change one piece of our data set. All right. Namely, let's say that instead of 550, this one right here, instead of 550, let's say this was, I don't know, 650. Okay. What does that do to the rest of our data? Now, nice thing about doing all these calculations in my calculator here is that I can hit enter in any one value, and I can go just change that one piece there. So if I do that, 650, then my mean, all right, it goes from 512 to 532, which doesn't seem like a really huge jump at all. But then I can go up here and grab this where I found my my variance here, and I can change this. And I'm just doing this to show you how this changes the overall events of what we're dealing with here, right? So this changes to 532 for all these values. So 32. I'm just changing all my means here. 32. 32. In this instance, I need to change this to 650. Just want to show you if we have one large value and all the other values are fairly close together, show you what this does to our variance and our standard deviation. And when we do that, that is a much larger variance. Before it was 770. And this is what it's telling us. 770 is a pretty small variance, which means that our data is probably pretty closely related to each other. Now we're talking about it 4670 is our variance. So then we do the square root of that value, and it tells us that our standard deviation is 68.337, which is a very large variance based upon the values we're looking at here. And if we were to recalculate what one standard deviation is above and below, when we do that calculation, what we will find in this instance is that all of our data, except for one value, 650, is one standard deviation from our mean. And then this one value of 680 here is actually going to be, well, it looks like it's going to be more than two standard deviations from our mean, because one standard deviation would take us to 580, and then another one would take us to 640, and then a third standard deviation would take us to 650. So we're actually talking about three standard deviations at that point. So just having this one piece that is significantly larger than all the others moves everything from being within two standard deviations of the mean to everything being within three standard deviations of the mean. And this is what this is telling us, is when we talk about standard deviation, we're saying that this is how much of a spread we have between our data. And the larger the standard deviation is, the larger the span is between our values. So a really large standard deviation implies that we have a lot of space. Our data is really spread out as opposed to being tightly formulated. So if we're looking for a particular drug interaction per se, and we find that drug 1 has a standard deviation of 27 and the drug 2 has a standard deviation of 68, it means that drug 1 is doing more of what we expect it to do than drug 2, because drug 2 has a larger span or a larger spacing of desired effects over drug 1. Okay, so that's how we can interpret those values, is we normally want our standard deviation to be smaller in comparison to the data set that we're dealing with. And having one outlier can have a pretty big impact upon the overall set, which is why sometimes we look at data sets and we say, oh, look, we have this big giant outlier. Maybe there's something we can do with this outlier before we do the rest of our calculations. All right, so thank you for watching. More videos to come. Please reach out with questions and comments, and take care.